I think we start with our today's discussion. So today, again, we talked of. This is the next part. So in the last lectures, last one or two lectures, we were talking, especially the last lecture, we were discussing about the energy bands, the origin of energy bands, and we have seen that solids, crystalline solids has three kind of energy band structures in principle, and those all those and how that was formed qualitatively we have seen. But remember the very first lecture, they said the engineering is all about quantitative quantification. So it is not good to say that there is an energy band exists and there is an energy gap exists one for different material. We need to know what kind of energy band. That means energy variation, the energy levels. There should be having a proper information about that. Then energy gap, which we have seen, and as you progress further, we will see as you study more about device physics, we will see that energy band structure and energy gaps are most important parameter as far as semiconductor material applications are concerned. The most of the applications of semiconductor materials are based on their energy band structures and energy band gap. So that's the most important parameter as far as the semiconductor electronics is concerned. So when you're talking of electronics today, it is semiconductors, semiconductors, semiconductors. The major role is played by the semiconductors. We'll see that there are some roles played by metals as well as insulators, but the major active devices are made of, majority of them are made of, or the major constituent of any microchip or a solid state devices are semiconductors. And for as far as the semiconductors are concerned, the most important property is their energy band structure and their band gap. So today we will try to understand again another aspects of energy band, like how we can quantify. And we are not going into quantification. That will need a lot of discussion, and it is time consuming, and we will not go into that. But how can you uh, estimate the energy bands? That is the theoretical formulation. We have seen the qualitatively. We have seen that. Can I quantify it? So so that is the first thing, and that will be very useful. And how it can be done, and what is the methodology used. Those aspects we'll touch upon that, and naturally physics will be our rescue. So physics will come very handy to do that. Have you? I mean, to before starting with that, I let me ask you: have you got any idea how to do that quantitative estimation of energy bands? Theoretical foundation for that. Any idea? Have you studied anything about it earlier? Yeah.
No, no, sir.
So I am also attending something which I have not uh, tried before. Like very often, we don't give much emphasis to these aspects, but I thought that let us try this also, like briefly. I mean, like today's presentation, we'll focus on that in order to give you an idea about how to go about the estimation of energy bands in solid. What is the methodology used? So, as I said, physics will be coming for our rescue. So, let us see. When we talk of physics, there are two major division in physics. As all of you know, we have. So, just let's go further. Yeah. So, you have generally, all of you are familiar with when you start a course in physics. We started with Newtonian mechanics. So, that is known as the classical approach in physics. The whole of physics, or the basically physics means study of nature of things. So the physical laws governing the system, they are normally given by Newtonian mechanics, or otherwise Newtonian mechanics is otherwise known as classical approach. So if you look into the Newtonian mechanics, Newton laws are written in terms of particle trajectories. Then we always talk of a particle or a body. So a particle is having an indivisible mass, and the variety of properties can be measured, and they are all observable. So you can observe those properties. So very often the most important parameters which we talk of is position and momentum. So these are the two things which we use to quantify the physics of, or the state of the system. Or the system means a collection of particles. So it can be a body, or sometimes you call it as a system. So they have various. So it means a collection of particles. There can be interaction between the particles, and they interact with the external world through external forces, and internal forces also could be there. So the state of the system is a collection of the states of the particles that comprise the system. So then we again assume that it is understood that all properties of a particle can be known with a, infinite precision. So precisely, without any uncertainty, you can know all the properties associated with that particle or of the body or of the system. So the evolution of the system or the state is given by Newton's second law. Newton's second law is essentially about the force equation and the force law. That means when you are applying a force, there will be a change in the system or the state. And then principle of causality, that two identical systems have same initial conditions, and when they're subject to the same kind of forces, their results will be identical, whether it is in Kurukshetra or whether it's in Cochin, or it will be same. The initial if provided the initial conditions are identical, and if you apply identical forces, then the net result will be same. So these are some of the things which are said in the standard or classical physics. This is popularly known as Newtonian mechanics or classical, or this approach is very often known as the classical approach. Now the question is, can I apply this physics to any system, whether it is because when the Newton's time, we were mostly talking of macroscopic bodies like planets, then very day-to-day things which we come across, whether it could be vehicles or things like that, because basically laws of motion and all those things. So these are all direct application of Newton's law. So mostly macroscopic. See, for example, you can design a vehicle or a spacecraft. All those systems can be, and the physics of all those things can be developed. The projectile motion, etc. All those things can be developed using Newtonian mechanics or the classical mechanics or classical physics. But the problem comes, the question arises, can I use it for microscopic systems? Microscopic system means we have some atoms, subatomic particles. What are the subatomic particles? Any idea? What are the kind of subatomic particles we talk of? Yeah.
So the atom inside, the particles
Yeah, what are
inside
the
it,
kind? So can you name some of the subatomic particles?
like sir, quarks,
Yeah, that is
electrons,
what is quarks?
neutrons. The quarks means the neutron and proton are made up of quarks.
No, actually, quarks are the supposed to be the most fundamental part as of today. Actually, this one thing we need to understand. It was a matter of energy. No, earlier we thought that electrons, then proton and neutron. Then it was found that if you have more energy, you can divide neutrons can be further, because that is why this high energy particle physics are known as high energy physics, because all it's a matter of binding energy. So the other name for high energy physics is particle physics. So as the particle physics progressed, so more and more energetic energy you could generate, then we have found that even the nucleus, there are so many subatomic particles like neutron. We have like all kind of baryons, leptons, or a lot of subatomic particles are there. I also don't remember all of them, so I am not. You can always see that. But quarks are supposed to be. There are again they are defined in terms of color and things like that. It's not associated with any color, but then normally they have. So the most as per the understanding of particle physics today, quarks are the most fundamental particles, because earlier people, what is the name of what is the meaning of the word atom? What is the meaning of the word atom?
Sir, first, when we started to study about the atom, then that was the smallest particle possible.
What is the meaning? That is the meaning of the word atom. Yeah, you are right. But then what is the meaning of the word atom? It is the meaning of this word is indivisible. So because people thought that it is the most fundamental particle, or what is like, but now today's atoms are not atoms. They can be divided into electrons, protons, neutrons, and then again all those things can be. So atoms are, it's a misnomer today. Atoms are divisible into electron. Of course there will be charge state and all those things. Atoms will be neutral because they have equal positive and negative charges. But the word literal meaning of the word atom itself is not divisible actually. So but then that is not true today. So when we apply those physics to those kind of Newtonian physics, there was some inconsistencies coming up. Again, you have these photons, the electromagnetic radiations, and phonons, which is the again, it is about the crystallography. Phonons will come. We will talk about it a little later, not today. So, but then this is a kind of things which. So very often, so when we talk of these subatomic particles, one important concept came, that is the wave particle duality. Actually, the matter can exist in the form of waves also, not only as the particle. This was basically postulated by Dirac. So wave particle duality came into play. So that brought us what is known as quantum mechanics. So we will today most of our discussion will be around this: what is quantum mechanics and how quantum mechanics can be used for our purpose. That is the idea. But this I am becoming very outrageous here, because there is a famous there is a famous statement. I think all of you can see. If you think you understand quantum mechanics, you don't understand quantum mechanics. It is a famous statement by this physicist, a Nobel laureate. Anybody can tell me the name of this physicist? You can see its photograph. Image is seen. All of you are able to see.
Yes, sir.
Who is this physicist? Anybody? Any idea?
Richard Feynman.
Yeah, this is Sir Richard Feynman, professor. So he has a lot of like very popular lectures he has given as a professor. Then collection of his lectures in physics is available. Feynman's lectures in physics, 3 part. It is available. The third volume is devoted to quantum mechanics. He was one of the most prominent quantum mechanics physicist, and he got Nobel Prize also for his work in quantum mechanics, quantum electrodynamics, or I think something like that. There was a Feynman diagram, and for some simplification. Anyway, so that is a separate thing. But this is attributed. Nobody knows when he made this statement, but most often this statement is attributed to him actually. He said that if you think that you understand quantum mechanics, then you don't understand quantum mechanics. So I am trying to explain quantum mechanics. That means I don't know anything about quantum mechanics. So this is an outrageous attempt by me to trying to define quantum mechanics. What is it going against the Feynman? So there is one more. Today, most of the people talk of Feynman in a different context. Any idea? Yeah, you have heard of Feynman in any other way? Hello.
No, sir.
Nanotechnology. Today we are migrating from microelectronics to nanoelectronics or nanotechnology. So then this his landmark lecture that was even before the microelectronics came into existence. That was 1959. Also, if I remember well, it was 1959. You can see that it's available on the net. It's a very popular lecture. So it was there is plenty of room at the bottom. That was the title of his lecture. So Feynman is quite famous by that lecture. Like most of the nanotechnology people give credit for the starting of nanotechnology to his that lecture. So he has so that anyway that is let us try to see what is quantum mechanics and how this quantum mechanics can be used to solve our problem. So that is what our focus today. So the first thing is, as we said earlier,
क्या वो सर डिस्कनेक्ट हो गए क्या?
हाँ,
अच्छा तुमको क्रॉप करनी है?
कहा तो था सर ने.
अच्छा अच्छा वो सर ने स्टार्टिंग में बोला था ना कि इनिशियल कंडीशन अगर सेम हो तो और मेजरमेंट में रिजल्ट सेम आएंगे, तो इसीलिए मेरा ये क्वेश्चन था. ये तो फिर टेम्परेचर और
वो
कुरुक्षेत्र
सर
और
ने कहा था,
हाँ,
अगर इनिशियल कंडीशन सेम है तो.
इनिशियल कंडीशन से मतलब ये हुआ ना कि एट सेम पॉइंट ऑफ टाइम वी आर थ्रोइंग समथिंग, है ना, या कुछ भी हम
कंडीशन सारी
एक्सपेरिमेंट.
कंडीशन जो भी कंडीशन है उसके ऊपर
तो
लागू
फिर
होती है, वो सारी
नहीं,
कंडीशन सेम.
ऐसे सर अगर बोल रहे हैं कुरुक्षेत्र में हो या हम कोच्चि में हो तो टेम्परेचर वेरी करता है, ह्यूमिडिटी लेवल वेरी
नहीं, तो
करता है.
सर ने यही बोला था ना कि अगर इनिशियल कंडीशन सेम हो तो. ये बोला था सर ने. इसी मतलब कंडीशन में तो सभी कुछ आ जाता है ना, टेम्परेचर
अच्छा,
भी सब कुछ आ जाता है.
यही सोच रही थी मैं कि टाइम एट सेम पॉइंट ऑफ टाइम की बात कर रहे हैं कि जो बाकी सारी एनवायरमेंटल कंडीशंस हैं उनको भी इंक्लूड करें.
देख, कभी एवी सर की तरह सर भी बोल रहे हो, सर को पता ना हो.
मतलब
ग्रुप पे डाल देते हैं.
हाँ, क्योंकि क्या पता सर बोल रहे हो और सर को पता ना हो कि पीछे से वो डिस्कनेक्ट हो गया है. जैसे एक बार एवी सर जैसे माइक ऑफ था और प्रेजेंट भी नहीं कर रहे थे. वही देखो, पहले बोला कि एक एटम होता है जिसको फर्दर हम डिवाइड नहीं कर सकते. फिर बोला कि एटम में न्यूक्लियस होते हैं. फिर बोला एटम के अंदर इलेक्ट्रॉन
हाँ वही
प्रोटॉन
तो,
होते हैं. फिर उसके बाद बोला एटम के अंदर क्वार्क होते हैं. फिर
तभी
उसके
तो
अंदर
उन्होंने
है
ये वाली लाइन
ना.
बोला, नहीं सुनो तो, तभी तो उन्होंने ये वाली लाइन बोला ना कि इफ यू थिंक दैट यू अंडरस्टैंड क्वांटम मैकेनिक्स देन यू डोंट अंडरस्टैंड इट, क्योंकि यही तो है इसमें.
Hello, are you
Yes,
able
sir.
to hear me? Yeah.
Yes, sir.
Yes,
Yes.
Yes,
sir.
sir.
I got disconnected. I did not know that. We were talking about quantum mechanics. So why this subatomic physics is known as quantum mechanics? So of course, the other one is known as classical mechanics. So two separate sections. When we are talking of macroscopic bodies, we talk of classical mechanics, which is essentially Newtonian mechanics. But when we come to quantum mechanics, the microscopic physics, we talk of quantum mechanics. Why the name quantum mechanics? Any idea?
So because there are things that we don't know in the quantum mechanics, and the results are very, very different from what we do in the classical world.
No. Why? What is the meaning of the word quantum?
That
Literal
will,
meaning of the word
uh,
quantum. That's what I am asking.
sir, does it relate with the word quantization?
So very small, something which is very small.
No. It is of course related to quantization. But then, what is quantization? So very often nowadays, this actually quantum is one term which is most abused or
Sir,
misused. Yeah,
sir,
tell me.
quantization, like we have studied the quantization of charge, means everything is like a multiple of integer.
Yeah, actually, it is packets. Actually, quanta is a packet. Actually, this you have
Okay.
discretization of energy. Actually, that is how. Actually, unlike Newtonian mechanics, quantum mechanics, many physicists contributed. Actually, so it's a collection of works of many people. Like it started with Max Born, the black body radiation. We'll not go into those details, but there the quantization of energy, because energy was considered to be continuous and all. There they have black body radiation. There the quantization of, or the discretization, like integer multiples of a fundamental unit. So that is what, just like he was telling. So the quantization of, from that it came. Actually, it's a packet. Actually, but nowadays most of the people use this, whether they are philosophers, they are metaphysics people. Metaphysics means philosophical people. Then even some of the doctors, you can, if you listen to some of this Dr. Deepak Chopra, uh, supposed to be a doctor in US. He very often give very popular lectures. So he talk of quantum healing, quantum leaps, and all sort of things. So it is one of the most abused word actually. But quantum means it is essentially discretization. So packets. The quantum means packets actually. So that is discretized packets of. It's not that one packet, two packet like that. No. So quantization essentially means discretization. So that started with the discretization of energy actually. So some integer multiples of one basic unit. That is what, if you look into literature, you will see that that is given by h into the nu is the frequency. So energy is equal to, so it will be multiples of h nu, 1 h nu, 2 h nu, integer multiples actually. H is the Planck's constant. So that is how all this started from there actually. Something around 1907 or so, it started like that, and a lot of efforts have gone in. Many people contributed. Yeah, photons are essentially quanta, packets of energy. Somebody is on the chat box. Somebody has run essentially photons. We started with photons actually. Yeah. So that is one thing. So that is how the name came. So now the other thing is, one of the most important, another main aspects of this quantization, quantum mechanics is uncertainty principle. This is again another physicist who has contributed immensely to the development of quantum mechanics. It is the Heisenberg. So in classical mechanics, we have seen that position and momentum. X is the position and P is the momentum. Both can be very accurately measured, precisely measured. There is no uncertainty. Whereas Heisenberg uncertainty principle says that if there will be, if you can't measure them simultaneously. of the microscopic particles. So this is very popularly known as Heisenberg's uncertainty principle. The uncertainty is h by 2 pi or something like that. So unlike there is a you see that there is an very important deviation from classical position. There the position momentum was everything, whereas here they are incompatible variables. So they cannot, like, simultaneously you cannot. So that is the particle trajectory cannot be, because in the classical mechanics the particle trajectory was given by position and momentum, whereas we say you cannot simultaneously get those two things. If there is one thing is known, the other, there could be uncertainty in the other parameters and things like that. So that there is an issue there. So this is another very important one, is the wave particle duality. Second thing is the Heisenberg uncertainty principle. Yeah. Now, so it's visible, no? The slides are visible.
Yes, sir.
Yeah.
Yes, sir.
Now, another thing is, this is again another important thing we need to keep it in mind. That is very often known as the correspondence principle. That when you go from microscopic to macroscopic or macroscopic to microscopic, then there should be classical laws could be transferred easily to the quantum, and quantum could be easily transferred to the classical. So when we are talking of quantum physics, the dimensions are of the order of 10 raised to minus 10 or so. And then when you talk of classical, it is of the order of few millimeters and things or beyond. So the large bodies, we use. This correspondence principle is another important thing. And now, how we go about the things? Because we have seen that what we have done in the classical mechanics cannot be used in the quantum mechanics. So how? So they again, it is to define the physical system. Quantum mechanics or physicists use of physical systems, or you are dealing with photons, conduction of electrons in metal, semiconductors. That our interest is, that is why I just mentioned conduction of electrons in metal, semiconductors, etc. That is our interest. It would be used in other physical systems also. When you, for example, when you're talking of nanotechnology, there we will be dealing with all kind of quantum phenomena. So we'll but current interest for us is conduction of electrons in metals and semiconductors. So we talk of a state function actually, and then so every physically realizable state of the system is described in quantum mechanics by a state function psi. So psi is a wave function. So because we have seen that wave particle duality is there, so the psi contains psi is a wave function. So physically realizable state means states that can be studied in laboratory, and accessible information means information we can extract from the wave function. So through using that wave function, we can extract the information about it. So the state function could be defined in terms of position, moment. But we have to, when we talk of position and momentum, energy, we should keep it in mind that position and momentum cannot be measured simultaneously. With there will be uncertainty. That's all. That should be kept in mind. So just let us see the difference between the way you go about it actually. So in the classical case, we talk of observable things like position. So there in quantum mechanics, we talk of an operator corresponding to that. So you define various operators, like for example, position is represented by an operator x. Momentum, we have seen that h cut is h by 2 pi. So then d by dx. The energy, actually, it is p squared by 2m plus vx. So this is actually two parts. There's a vx is the potential energy. Yeah. So this is another important thing. Now, the most important contribution to quantum mechanics came through, I mean, he has combined like whatever happened between Max Born, Heisenberg's, everything. And he has combined many of those efforts and give a formal form of quantum mechanics. So when we talk of quantum mechanics today, we talk of Schrodinger equation. So that is the fundamental equation. Just like Newtonian equations are used to define the state of a physical body. So, and when you talk of the microscopic body, Schrodinger equation describes the evolution of the quantum mechanical system. So this is very often known as the Schrodinger wave equation, SWE. So it represents the quantum equations of motion. Motion means the evolution. It's not necessarily, don't consider it as just like the motion in the case of Newtonian equation. So it is the equations, evolution of the state. That is the meaning of the motion here. So you have this kind of a form. This is the fundamental equation. It's one-dimensional one I have shown here. So only x coordinate is. So this is the fundamental, and the psi is the wave function, and this. So this is a kind of a partial differential equation, and solution of psi will give me. So the solution is very often known as the eigenstate. So this is an eigenfunction. There are various conditions an eigenfunction has to satisfy. So the solution of this partial differential equation for this potential, just 1 second. Hello.
Yes, sir.
Hello.
Yes, sir.
Hello. Yeah. Sorry, actually, somebody had come for home delivery. Yeah. So I just so sorry for that. Yeah. So solution of this Schrodinger equation will give us the different parameters of interest. That is the whole idea of the Schrodinger equation. So the things come down to this thing. It can be time independent and it can be time dependent, independent Schrodinger equation. Dependent. Suppose you want to see the transient effects, it has to be the time dependent Schrodinger equation. And if it is time independent, then of course you need to solve the time independent Schrodinger equation. So that is the basis of quantum mechanics. It's a fundamental equation which is used. So it looks very simple. Uh, see, actually, we have in during my masters, we used to have maths involved is very simple here, but the solutions are and a bit complicated. Even for hydrogen atom, we have done it in for hydrogen atom. The whole analysis used to go around 10-15 pages actually. So for a single atom, and so you can imagine when large body of systems are there, then the solution becomes complicated. But Schrodinger says that this equation it should be properly formulated and solved. Then you can understand the whole physics of this. And this is the fundamental equation which is used for all your IT revolution. So quantum mechanics is the fundamental thing for all your IT revolution, actually. So this is the basic thing in quantum mechanics, that Schrodinger equation need to be solved for the given case. Any question?
No, sir.
You are able to get some sense of it,
Yes,
what
sir.
we are talking? Yeah. So
Yes, sir.
now let us try to get into our problem. So the important thing is, first we need to formulate the Schrodinger equation. That means the most important thing to solve the Schrodinger equation is we need to know the potential associated with the system. So solving the Schrodinger equation for that particular case means that particular physical system, the potential should be known. So now let us come to our problem. So this is again this is way of another way of writing the Schrodinger equation. H is the very often in classical mechanics it is known as Hamiltonian. So psi is the wave functions. Hamiltonian is nothing but the total energy. There are one is the kinetic energy kind of thing, and V is the potential energy or V. So TH Hamiltonian is to be formulated, and then psi need to be solved. So this is another way of saying it actually. So in classical mechanics, very often people talk of Hamiltonian. So same only thing is the when you come to quantum mechanics, the way it is written is slightly different. That differential form, the psi becomes a wave function and things like that. Yeah. Now coming to our problem, just try to see this. So you have single atom, you have one like Bohr atom model is there. Again, you can solve the Schrodinger equation for single atom. Now our question is, our problem comes down to solving the Schrodinger equation for a solid. Now let us see. You have there is a periodic arrangement of atoms. I think you get this figure is visible, so you can see different atoms. There's a potential distribution around that. Blue lines showing the potential distribution. The top figure shows that the potential distribution as you go away from the one atom, that variation in the potential is shown, and probably the outermost shell electrons. But when you are bringing atoms together, there will be a change. So you see that there is a periodic potential variation, periodic change in the potential. So you see that to the left side, we are simplifying it into a kind of rectangular potential kind of thing. So it's region there is a potential, and then region there is no potential exists. Like you can make out. So I am approximating the potential of a solid to this. So this is this model of solids are known as Croning-Penning model. Croning-Penning, they have talked of a periodic potential, because the periodicity is represented in the physics as a periodic potential, because we have seen that crystals have a periodicity. That periodicity is giving rise to your periodic potential. So our problem is simplified to solving the Schrodinger equation for this kind of a periodic potential. So that helps us in finding the uh, energy band, because basically what we are talking is the energy distribution or the energy states available for this electron. So we need to know that. So we are solving Schrodinger equation for electrons when they are moving in the solid under the influence of this periodic potential. So we find out the periodic, if you know the periodic potential, we can solve that. Solve the Schrodinger equation, and then solution of the Schrodinger equation will give me energy states available, and that is essentially the energy band structure. This is the principle used in solving the in finding out the energy band structure theoretically. Okay, any questions?
No, sir.
So try to understand this. So this is the essential concept is shown here along with the Schrodinger equation. Yeah. Yeah. So a little more. So you have seen that. Okay. So the periodic potential of the crystal is given by the red line now. Periodic potential. So this is an approximation we are making. So that is essentially the Croning-Penning model. So solving this Croning-Penning model will give me the energy band. That is the idea. So you can solve it. So you can write down. So you can write down the equation and solve the periodic potential. So once the important thing is we need to know the periodic potential for corresponding to the problem. Suppose, for example, we are doing it for silicon, we should know the periodic potential, but that can be known actually. There are methods available for finding out the periodic potential. So once we know the periodic potential, one can solve it. So very often we take advantage of the unit cell. So within that, then we see the periodic variation in the potential. So you can take, so you need to solve in the unit cell, and then you can extrapolate and extend it to further. So that all those kind of manipulations are done. So one can do that way. So that is the essential thing. So once we solve this, we get this kind of form at the lowest level. We get it's not as simple as this, but at the lowest energy cases, we will get this. And this is very often known as, any idea what is K? What is K?
So position.
No, K is not position. Anybody else?
Momentum, sir.
Actually, it is related to momentum. It is not momentum. K is the wave number, actually. So how will you find
Okay.
out the wave? What is the relationship between the momentum and the wavelength? This is K is known as the wave number. But what
They
is
are
the,
inverse of each other.
pardon?
Wavelength is 1 upon wave number, I think.
Yeah. So actually, and what is the relationship between the wavelength and momentum? See, wavelength of the particle or electron or whatever can be found from, if you go into deep, it's again from de Broglie's concept, is H is the Planck's constant, H by P is the momentum. So H by momentum will give me the wavelength, and K is the reciprocal of that. So I can relate it to momentum. So what is, you are seeing this left side one equation, Ek is equal to H cut squared K squared by 2m. What is this? What is H cut K? H cut K squared by 2m. What is this? Any idea? Hello? Hello?
Yes, sir.
Yeah, what is this?
Cut is,
What is this? Are you familiar with this relation? Ek is equal to H cut K squared by 2m. You are familiar, but you are not able to connect actually. It is,
sir,
we
Sir,
can,
half mv.
yes?
Sorry.
MV square, half MV
Half
square.
Pardon?
mv in square.
Hmm?
Sir, half mv square.
I by 2m? What is it? Actually, it is P squared by 2m. Energy is related to momentum by P
Yes, sir.
squared by
Yes.
2m. So
Yes,
that
sir,
is
yeah,
what is.
yeah.
So it is. So that is how it is momentum actually. Energy is written in terms of momentum. Okay, and K is the, I told you, K and momentums are related. So that is why it is basically K squared, P squared by 2m. Energy is related to, you can find out. Any disagreement there? Hello?
No, sir.
Yeah.
No, sir.
So we see that energy band diagram is coming in terms of EK diagram. So that is why energy band diagrams are essentially known as EK diagram. That is energy versus momentum of the system actually. So that is how this things comes. But then it is not as, here it is showing to be parabolic. There will be deviation, and this energy, this is a very simplified uh, form of energy band. And then we see that in the right, actually, which is not M, it should be M star. So in the next discussion, we'll be talking of that. We will be talking in terms of what this is. There is an essential difference between M and M star. What is the difference between M and M star? Left hand side, I am writing 2M. The right hand side, I am writing M star. What is the difference?
Sir, it is effective mass.
Yeah, that is a very important concept in semiconductors. That is the effective mass. So that a little bit about that we'll be discussing in the next discussion. So we see that essentially energy band diagrams are nothing but EK diagrams, energy versus momentum. So there are very important concepts involved and very important implications of this. Uh, this so this So that is the fundamental thing. Yeah, that this way I can solve using Croning Penning model. I can solve the Schrodinger equation and get the energy band structure of the different materials. So what I need to know is the potential corresponding to that material and solve the Schrodinger equation. Of course, when you talk about differential equations, you need to apply the boundary conditions, and applying suitable boundary conditions, I can solve it. People have done that, and so we are not going into those details. But any solid state physics book will give you all those details how to. So in this case, somebody who is interested, they can go through this electrons and holes in semiconductors by William Shockley. There is a chapter devoted to all these calculations and all those things. One can go through that, but we will not be. Only my idea was to give an idea about how to solve how you can get the energy band structure of materials using Schrodinger equation. So that was the idea. So Schrodinger equation as well as the periodic potential or the Croning Penning model helps us in doing that. That was the idea. Yeah. So I think we will wait, pick up some questions, and then today's session I'll wind up. It was a brief discussion only. So let us see. Yeah, first I will wait for your questions, and then because I expect some questions from your side, and then I'll get into my questions. Yeah.
Sir, from the last slide,
Mm.
you have
Yeah.
shown the band in the second diagram. You have shown the band which we need. Can you explain it?
Pardon?
Yes, sir. Can you explain the second diagram?
The right hand side.
Yes, sir. The right hand side.
Yeah, actually, what is like if when you apply the boundary condition, you apply a periodic boundary condition. Every like if you solve the I did not go into much detail because I thought it will be like you will get into like many of you may not like that. Actually, when you solve the Schrodinger equation for using Croning Penning model, you solve it in the full crystal you can solve. So what you do is you take a unit cell. So the boundary condition you apply is periodic boundary condition. So every pi by a or minus pi by a, that is a is the lattice constant, that is the interatomic distance. So then there is a periodicity. So you can take advantage of that, and you can bring it into a single zone, that is known as the reduced zone. Instead of going the whole material, you reduce it into a single zone using the periodic boundary condition. So that way you get, and there is a energy gap in between. So that is what is shown here. So it is in the reduced zone or within the first zone, and then you have that is repeated. Otherwise you will have I don't have the diagram here, probably in the next, otherwise it will be going further. So that is what is shown here. Is it clear?
Yes, sir.
So you are using the periodic boundary condition actually, because every interatomic, every distance a, that is the interatomic distance. Actually, when you solve it, you will get a sine cos function. Actually, when you solve this Schrodinger equation, you get a component. So it will be periodic because sine cos means it is a periodic function. So the periodicity will come every interatomic distance, that is a. So it will be coming in terms of minus pi by a actually. So that you bring in that concept. That is why this kind of thing. So there is a discontinuity at a, and then again you have again the same kind of thing is repeated. So that is why you have energy continue of energy band. Then you have energy gap, things like that. That is what is happening. Yeah.
Okay, sir.
Sir,
Yeah.
sir, what is that purple line which is going up and down?
Purple line is, so that is if you don't apply the periodic, you're talking about the right hand side where it was going further straight. I mean the in the parabola or coming down.
Sir, in the parabola.
So actually, if you don't apply the periodic boundary condition, you are extrapolating it actually. You are going straight, actually assuming that it is going like that is the assumption. But we are applying the periodic boundary condition, it doesn't happen. There is a discontinuity. It will not be continuous. That other one is simple extrapolation of the first zone actually.
Okay, sir.
Yeah. So that is an
Yes.
extrapolation. Yeah. Without any break, you are just extrapolating. Yeah. So, but then in reality, it is not so. Yeah. So, any other question? So actually, if you want to find out the energy states of any, because it's very important in nanotechnology, one can solve the Schrodinger equation for that particular system and get, because increasingly Schrodinger equation, especially for even for microelectronics people, solution of Schrodinger equation becomes very important. For example, your dimensions or your device dimensions are in that range actually, where the quantum effects are coming important. So you need to solve the Schrodinger equation today to find out the transport of electrons in devices even. Earlier we were using it only for getting the energy band structures, etc. But today our dimensions of our devices are few nanometers. So there, even in the microelectronic devices, we need to solve the Schrodinger equation and things like that. So this Schrodinger equation playing a very important role in all these things. Yeah. So any further questions?
No, sir.
I have one or two questions to elaborate a little. So we talked of two kinds of. I'm not showing you the questions, so the questions are visible to me. Uh, so my first question is: we talked of classical mechanics, we talked of quantum mechanics. Is there any other formal form of physics other than these two? You got my question. We very often talk of classical mechanics. We talk of quantum mechanics. So any other one other than these two?
Planetary.
The planetary is basically covered with Newtonian mechanics, no, because a large body. Which is not cannot be accommodated any of these two. Something. Got my question? A system which cannot be described by any these two. So you need something different.
Sir,
Yes.
black holes.
Pardon?
Sir, black holes.
Black hole, actually, what is the kind of it is used there? So what is the kind of physics used there? So that brings us one of the great physicists of 19th or 20th century. When you talk of a physicist of 20th century, whose name comes to your mind, according to you?
Sir, relative
Stephen
mechanics.
Hawking.
Yeah, Albert Einstein. So Albert Einstein's work, theory of relativity. Actually, when the particles or anything moving velocity comparable to the velocity of light, then there is a change in mass, because this here we have say, okay, in quantum mechanics we have considered the wave nature of the particle. Then in the classical mechanics we have talked of the attributed a mass, and mass is supposed to be constant. Whereas when the particles are moving with the velocity or appreciable velocity, you cannot approach the velocity of light, but when the velocity is very high, is comparable, there is a I'm not going into those equations. You can see those equations, how the variation of a mass happens with the velocity comparable to velocity of light. Then the change in the time as a coordinate, time dilation we talk of. Actually, you can come today and come back yesterday. So that kind of time dilation is possible. There is a beautiful movie using this concept, sci-fi movie, that is Inception. If you have not seen, it will be worth
Yes, sir, we have seen it.
yeah, so you can see that daughter is getting older than the father and things like that. So all those very interesting thing happens. So then, so that is a different kind of I mean, is an extension of this given by Einstein, that is theory of relativity. So there, that also comes, that is another kind of physics where the motion of the particle uh, is considered. Well, of course, motion means when the velocity of the particle is appreciable to the velocity of the light, and the maximum velocity within this under this formalism is the velocity of light. And then another important uh, derivation from that is the energy and matter are interconnected. E is equal to mc squared. One of the most famous equation. E is equal to mc squared. That is, energy and matter are the two different forms only. Matter can be converted to energy, and energy can be converted into matter, etc. So all those things comes into play there. And according to Einstein, that is the max velocity of light is the maximum velocity, and you cannot. So anybody who can bring in a particle whose velocity is greater than the velocity of light, there will be a breakdown of Einstein's theory. So people have been looking for it for the last many decades, actually. So that is another physics one need to consider. But of course, in our case, that kind of things are not happening. The velocity of any of these carriers are not to that high, so we need not worry about that. And there's a second question already we have discussed. How can you find the wavelength of the particle? We have seen that if you know the momentum, h by
M.
momentum will be give you the lambda, and k is the 1 by lambda actually. So that is a wave vector, with the wave number we talk of. So wavelength of the particle is given by Planck's constant divided by the momentum. So what about the momentum of the photon then? Photons.
Under root of 2mk.
Yeah, actually, why no? Me, how it can be there? Has photons got any mass? The photons cannot be having any mass actually. If they have mass, according to theory of relativity, they will become, when they move, mass will become infinite because they move with the velocity of c actually. So photons have no rest mass actually. They don't we don't consider any mass associated with the photon. That is again a very important concept, that this electromagnetic radiations or the photons, that is a quanta of electromagnetic radiation, is known as photons. Photons are considered to be massless, so we don't consider any mass. Now, today's last question. We have discussed some of these quantum principles like wave particle duality, and then this correspondence principle, then Schrodinger equation, etc. Any other quantum principle you are familiar? Any other than what I have discussed? Yeah, that is, it is not there in classical mechanics, but it is there in quantum. This is a very important physical phenomena, actually. Yeah. Hello, got the question? Hello.
Sir, can you repeat, sir?
The question is, any other quantum principle you are familiar with other than what we have discussed? I have not discussed about it, which is very common quantum phenomena, which is not described by classical mechanics. Actually, only in quantum you can discuss or elaborate that, or you need to use quantum mechanics to understand that. What is that phenomena? Got the question?
Yes, sir. When we throw light on the metal, then uh, the electrons are excited and somewhat like that, a
Yeah.
formula. I didn't remember the name exactly.
Photoelectric effect. So that anyway is showing
Yes,
the particle nature, but then that is no, I mean that is well explained even with the classical one we can explain photoelectric effect. We need not bring in the wave nature also for the to describe the photoelectric, because in fact Einstein got his Nobel Prize for photoelectric effect. Actually there's a lot of studies in the photoelectric effect, actually 1907 I think, 07 or 14, I don't remember the year, but that was his first work actually, photoelectric effect and things like that. Yeah. Anybody else? Have you heard something called tunneling? Hello.
Yes, sir.
yes, sir. Yes, sir.
Yeah, tunneling is particle cannot tunnel. Only the waves can tunnel. So this is, and we have used tunnel diodes. Then in nanoelectronic devices, we very often use tunneling phenomena. So tunneling is an important phenomena where the wave function is used. So that physical principle or property can be explained only on the basis of quantum mechanics. You cannot explain it on the basis of uh, uh, classical mechanics. Then another one is, which is very important, because I don't want to go into the details, but still quantum computing, where you use quantum entanglements. You have see today we use binary system 0 1 and etc. We don't have the combination of this. So there the mixing of states take place. That is known as quantum entanglement, and all kinds of things. So that is used in quantum. So you can, instead of bits, you use qubits. So you have more than one or two variables are available for your manipulations and things like that. So very interesting things happens. So there are some of the other things where the quantum principles can be used. Yeah. Any other questions?
No, sir.
So I think we'll stop it here today. So what I will do is, in the next class we will wind up our discussion on the energy band. I will show you the actual energy band structure of some of these materials. I mean, just to show. We will not go into the actual derivation and all those things, because we have seen that we can use this Schrodinger equation coupled with the periodic potential and solve it, and so we get the see the solution, and then we will get into the electron carrier how to find out the carrier concentration using the energy band structures, and then we go into the conductivity and things like that. So, and then we in between will be discussing, when once we have the energy band structure, we can talk of direct and indirect band gap materials, etc. So we'll just briefly touch upon them also. All those things we'll do it in the next. Okay, thank you.
Thank you, sir.
Thank you, sir.
Good.